So this is our implementation of the ECE 4305 project for Bluetooth Low Energy so far. So to begin, after we define some initial general system details, such as our sample rate, any sort of upsampling, downsampling factors, and our sampling per frame, we proceed into some of the basic Bluetooth parameters. For this method, we're using the LE1M, which is the standard 1 megabits per second, as well as a channel of 35. The typical preamble for the LE1M, which is an alternating pattern of zeros and ones for 8 bits. The PDU length in bytes of 257 and a CRC length of 3 in bytes. We combine those together to create the data no header as it's defined at the bottom, which is the combination of the raw data, which for this case is all ones, and then a CRC, which is going to be a 0 vector. After then doing some impairments, we're going to span from an SNR value from 0 to 20 incremented by 1. We're going to do the transmission of the data, which is going to be performed using the BLE waveform generator, which is going to take in the data to be submitted, our BLE mode, which in this case is the LE1M, our channel of 35, and our samples per symbol, which is going to be 8 samples per symbol, with the access address that we have defined. And continuing through, we're going to do an iteration across our SNR values. We're going to inject some additive white Gaussian noise into the waveform. From there, we're going to put an offset frequency to it, which will simulate any local oscillator differences between your transmitter and your receiver. And from there, we're going to go down a little bit further, and we're going to start to look into the receiver side. From there, we're going to begin by doing the AGC, which is going to be our automatic gain control. We're going to have it so that its desired output power is 1. From there, we're going to correct for any offset, DC offsets, which is done by taking the mean of the signal and then subtracting that mean from each individual index. From there, we're going to go into the fine frequency compensation to correct for those adjustments that have been made to the channel. And then we're going to proceed into our match filtering, where we're going to use the GMSK convolution of the filter with our data, where we can then take that data and we can begin demodulating and decoding, and then de-whitening the packets such that we can get the binary data that we have implemented into it.
Now, to test this method, we utilize the script that goes through this the same process, but instead utilizes a little different bits of code. So, as you can see here, we defined everything up here similar to the previous function. We can see that we keep the signal-to-noise ratio the same. Samples per symbol is 4. Data length is 42 bits here, and we're just going to simulate 2 of the 5 modes, LE1M and LE2M. So the way this simulation works is that we're going to simulate through different, the different like LE1M and LE2M, and we're going to iterate through a number of packets and develop a max number of errors, and we're going to be able to see the bit error rate and the packet error rate as we keep going, and that's what's initialized here. We also have a bits per byte defined here. So this is from similar to the previous file, but as we can see here, we have our access address as the address we defined from our initialization. Now we're iterating through the modes, so this will be LEM1 and LEM2, and then we'll have this vector which transforms the SNR values into values that will be able to be calculated. And then we're going to iterate through all of those SNR values from 1 to the length of the vector. So to do so, we have to go through a couple we have to define a couple of objects. So one of them is error rate, which is going to be used to calculate the difference between the transmission bits and the received bits. Here we have an init, which is helper BLE impairment init. And these define a bunch of the receiver parameters, which you can find via just right-clicking it and looking through it. But it defines a lot of important aspects of the receiver, which we plan to implement ourselves when we do the hardware side. And the same thing here for the helper BLE receiver init. That's where we define a lot of the receiver impairments. So correct me, I I was wrong. This is just impairments. This is an object that they use. This is what they use to define the receiver things. So before we go into the while loop, which does all the communication, we just define the number of errors and per count and number of packets, which are used to calculate bit error rate. Then, similar to the previous file, we take our bits, we transform them into int8s, and then we define them as our transfer bits. Then we set a random channel, and then we have a TX waveform, which is again defined by the BLE waveform generator. And as you can see in this graph right here, this is the result from the spectral analyzer of our TX waveform. Continuing down, one of our issues with trying to implement this was trying to implement our own impairments. We tried to implement that, and the way that it was calculating BER and PER was not working. So what we used here were some predefined frequency offset and timing offset, which would then be corrected and which would then be applied by this helper BLE impairment addition. And then we'd send that signal through the Gaussian white channel through this function right here. And then similar to the way we applied the practical receiver, this utilizes a practical receiver, which goes through many of the same processes. So you have, again, the gain control, DC offset, coarse frequency offset correction, match filtering, time recovery, and all of these other aspects, which are very similar to the way we did it, but just using a different type of MATLAB object. Now down here is where we calculate bit error rate and packet error rate. So we go through the length we just make sure that the length of the transmitted and received bits are the same. And then we define the errors as using the object error rate to compare the two. And then we define the bit error rate directly as the result of this object right here. And then we have this number of errors in the current pack, which is defined here. And if there are any errors, then the PER count is added, which means that a packet has error in it, and we're going to continue, and that's going to continue through the calculation. Then we have number of errors, which is error at index 2, and then after that the number of packets increments. And then through here we're able to calculate the PER. So at this mode, at this SNR, we're able to calculate what the packet error rate is. And down here represent a couple ways that we represent this, including here where we're able to graph it, etc. So we'll show you right here on the command window, going through the calculation. Oh, try that again. So see right here, the BER is slowly going down the higher the SNR rate, and we see that the PER is also going down. We'll be able to see that right here. It'll go up to 20 decibels, and then it'll go right back to 1 for LEM2, which we see right here. The PER is going to be 1 for quite a bit, and then drop around 8, 9, and then by 10 or 11 it should be back to 0. And then coming up, you should see the relationship between increasing SNR and the packet error rate and the bit error rate. So once that's done running, you should see right here. This graph shows first as the bit error rate decreases as the signal to noise ratio increases. Same thing for the PER. So for the future implementation, our focus is to kind of implement this method of PER and BER to our own program and be able to apply this method of receiving the signal via hardware code into our Plutos. So that's our implementation. Thank you very much for your time.